All right, so in this example, we're actually going to go ahead and show that these two numbers, so in this case, the numbers 512 and 251, are what's referred to as relatively prime. So if you look underneath this piece of terminology of relatively prime, I have another piece of terminology that means the exact same thing. So in this case, I'm using the term coprime. And this is one of the kind of somewhat unfortunate things that we see in mathematics and discrete mathematics and computer science is that at some point in time, there were, in a sense, two different groups of people studying the exact same thing. Group 1 gave it one piece of terminology, and Group 2 gave it another piece of terminology, and both of them in a sense stuck. So you have kind of a bunch of people that still use this term relatively prime and another group that's going to use this term coprime. So it's just kind of just making you aware of some of the kind of awkwardnesses that exist in higher level mathematics, is that depending on your author or your source material, you may see one piece of terminology which is actually describing something that you've been working with for a long time. You just happen to call it something else. So in this case, I actually do use these two pieces of terminology in a sense interchangeable, though I do actually prefer the term coprime to relatively prime. I think it sheds a little bit of information into what's actually going on. But in any event, these two things are actually talking about this idea of if I'm given two numbers, I want to really start to study how are these things going to be similar or how are they going to be different. So this world of being relatively prime is chatting about divisors. And in particular, I'm going to say that the largest thing that divides both of these things is simply going to be this nice little number of 1. That is, I'm going to have that the greatest common divisor, or this GCD, of 512 and 251 is simply going to equal 1. So we know that 1 is going to divide every single number that we're ever going to be interested in studying. So we know that this greatest common divisor is always going to be at least 1. So in this case, what's happening is that I'm actually equal to 1. So what that's saying is that there's going to be no other divisors larger than 1 that divides these two things. So in this case, I have that these numbers are in a sense blind to one another. I have this 512, which has a whole bunch of divisors, and 251 has some divisors, but none of those things match except for this one little special number of 1. So the kind of somewhat unfortunate thing that we see in this world is that the word prime exists in both of these pieces of terminology. And that sometimes throws students off because if you look at this number 512, you obviously see that that number is in fact not prime because 2 divides that thing. So that's kind of the somewhat awkwardness, is that I'm going to have these two numbers that are relatively prime even though one of them is obviously not prime. So in this case, the number 512. What it is saying though is that if you look at the world of the divisors of these things, they don't interact at all. So in a sense, comparing 512 to 251, it pretends or it kind of acts like it's a prime number because none of those divisors actually match. So it's kind of a somewhat unfortunate world that takes a little bit of practice, or at least kind of burning that into your brain of this word prime does not always mean what I think it means. And that's where you have this idea of relative. So in the world of if these are the only two numbers that exist, they are in a sense prime to one another, or kind of grouping them together, they are going to be prime. Okay, so I'll get off my soapbox chatting about terminologies and things like that. Otherwise, we could go on and on and on chatting about things that are just kind of, I don't know, some person created this terminology and for whatever reason it just kind of stuck. So in this case, we have a couple different ways we could actually show that this GCD is in fact 1. But we just got done chatting about this Euclidean algorithm, so we might as well give that thing a shot just to kind of see another example of all those little workings. So what I'm going to do is I'm going to look at this pair, so 512 and 251, and I'm going to run this division algorithm a few times all the way until I get to kind of this last non-zero remainder. So in this case, what I want to do is I want to see how many times does 251 actually go into 512. Well, I know that if you take 251 and multiply it by 2, you're going to be up to 502. So you know that you're 10 away from that kind of magic number of 512. So in this case, I'm going to have that 512 is 2 times 251 with a remainder of 10. So what's going to happen here is that this little divisor of 251 and that new remainder is actually going to become my new pair. So in this case, I'm going to kind of chip away at this thing, creating smaller and smaller pairs as I go. So what's going to happen is that I'm going to bring this new pair, so this 251, comma 10, and I'm going to run this division algorithm again. We again know that this kind of column that exists over here is going to have this really special property that they're always going to have the exact same GCD. So as I get smaller and smaller, it's hopefully going to be easier to see that I'm going to actually in fact have the only thing in common being a 1. So in this case, I'm going to run this division algorithm one more time. So I'm going to look at 251 and the number 10. So I'm going to think about how many times does 10 go into 251? And in this case, that's going to be what? 25 times, because 25 times 10 is 250, and then I'm going to have a remainder of 1. So in this case, I'm going to have 251. Here's my 25. There's my 10 with my little remainder of a 1. which in this case is a 10 and a 1. So at this stage you could actually stop, because you can see that the only thing that is in common between this 10 and the 1 is going to be that number 1, because one of the numbers is in fact 1. But if we really wanted to do that last step to actually see that remainder of a 0, again, that's kind of the nice little thing if you're working in the coding world, that gives you the nice exact stopping point. You run this thing until you see a remainder of 0, and then you go back to the last non-zero remainder. So in this case, I know that 1 is going to go into 10 10 times, because 10 is equal to 10 times a 1 with a remainder of 0. So the moment you see that remainder of 0, you stop, and then your GCD is going to be that last non-zero remainder, which is exactly what I wanted to see. I wanted to show that the GCD of 512 and 251 is in fact equal to a 1. All right, so let's check to make sure that I did it correctly. There's my kind of filled out notes version of this thing, which is nice to see. Okay, so what's going to happen is that I'm going to take this little process, and now we're going to run this thing in reverse. We're going to create what's referred to as the extended Euclidean algorithm. And what this is going to be useful for is it's going to be looking at answering this question. The idea is that if I know that two numbers are actually going to be relatively prime, I'm going to be able to find two integers, in this case x and y, that solve this little equation of 512 times x plus 251 times y is going to equal a 1. And we're going to chat about what makes this actual equation really, really useful. It's going to come back into our kind of playing into this kind of hand of trying to solve some congruences and looking at inverses and things like that. So for now, you're just going to have to believe me that having this equation is really, really useful. So it's actually pretty easy to get to this equation to actually find these values of x and y. What we're going to do is we're going to take this kind of nice giant grid that we have over here, and we're going to work backwards. So what I'm going to do is I'm going to start with that little equation right there. So what I'm going to have in this case is I'm going to have that the number 1, so if I solve this equation for 1, I'm just going to bring this 25 and the 10 over to the other side. So I'm going to have a 251, in this case minus, so I'm going to subtract off a 25 times a 10. And that's going to be my starting place. So you're going to see that that little 1 right here is exactly what I want to see at the end of the day. You can see that there's going to be this 251 coming into play, and what I want to do is I want to somehow change this thing into this component that's going to involve some 512s. Well, the idea here is that I'm going to work with that second equation that I have if I'm kind of working in the reverse direction. So it's actually that first equation that we're working with. What I want to do is I want to somehow replace that little 10 that I see in this component with another representation for 10. So what's going to happen is that from this equation, I can see that 10 is equal to 512 minus a 2 times a 251. So what's going to happen is I'm going to take that component and substitute it into this little 10 that I see right here. So in this case, I'm going to put that all in green because it's kind of nice. So in this case, I'm going to have a 512, and there was a negative 2 times a 251. Okay, and then I'm going to bring down all of that purple stuff that I had before. So in this case, I'm going to have a 251 minus a 25. Okay, so now I just got to clean this up a little bit. You're going to see that I have my 512s, I have my 251s, I just need to group all these things together. So distributing that negative 25 is then going to give me a negative 25 multiplied by a 512, and then in this case, I'm going to take that negative 25 and multiply it by that negative 2, which is going to turn into a positive 50, and then there's going to be a 251 in front of that. So here you can see this component that's going to have that 512. Here's some stuff that has a 251. Here's some stuff that has a 251. Officially, I have one of them over here. And if I add it to the 50 that I have over there, is going to say that I'm going to have 51 of these 251s. And then there's going to be negative 25 of these 512s. And these are going to be added together in this case. So you can see that this is exactly what I wanted to see. I have some number. So in this case, what do I have? I have the negative 25 multiplied by 512, so that's going to become my x. And then on the other side, I'm going to have this other number, in this case 51, which is going to be multiplied by my 251, so that's going to become my y. So in this case, letting x equal negative 25 and y equaling 51 is going to solve this equation that I have up above. And that's a really nice thing to see. We're going to kind of dive into why that's actually nice in kind of a little bit. It's going to, as I mentioned, come back to this world of modular arithmetic and actually trying to solve some of these things. So in this case, let's just double check what I have in my kind of filled out notes to make sure that I'm not lying to you in this case. I did try to keep these things somewhat color coded. So the idea is that I'm going to have that little 1 that I'm looking for. So that's what's going to come up from that last step of my Euclidean algorithm. And then I'm going to work backwards. So in this case, I subtracted off that 25 times a 10. That little 10 was actually that remainder from that first step. So I'm going to solve now for that. So in this case, I subtracted off this 2 times this 251, and then it's going to get substituted back in. So that was that step that was all done in green in this last example. And then what I'm going to do next is I just simply distributed that negative 25. So in this case, the negative 25 times the 2 makes a positive 50. And then I lumped these two things together, giving me that factor out in front of a 51. And the other one's going to have that coefficient of a negative 25. So in this case, if you let x equals negative 25 and y equals 51, you are in fact going to solve this little equation. So the question in this case is, why do I care about something like this? How is this useful? Why would I kind of ever want to use anything like that? So I think I'm going to pause this video and actually jump into that example in this next video. What's going to happen is that we're going to use these two particular numbers to actually go ahead and attack some of these solving congruence problems. So the problem that we're going to be attacking is something like this. And the problem is going to be, I want to get rid of that 51. And we're going to actually use this information that we have here to actually show us how we can get rid of that thing. So I'm just going to pause it now to kind of give you a little breather to dive back into this example.